Welcome to this coding problem walkthrough. Today, we'll be tackling problem number 138, copy list with random pointer. This is a fascinating problem involving linked lists and random pointers, which is both challenging and rewarding to solve. Let's dive in and explore the approaches to solve it. In this problem, we are working with a special type of linked list where each node has two pointers. The first pointer, called next, connects the node to the next node in the list, forming a sequence. The second pointer, called random, is unique because it can point to any node in the list, including the node itself, or it can be null. The task is to create a deep copy of this linked list. A deep copy means that we need to replicate the structure of the original list using entirely new nodes. The new nodes in the copy should mirror the same connections as the original, meaning the next and random pointers in the new list must point to corresponding new nodes. The input and output representation of this linked list is a series of nodes, where each node is described by two attributes, val, which is the value stored in the node, and random_index, which indicates the index of the node that the random pointer points to, or null if the pointer is not set. To help you solve this, a node class is provided with attributes for the value, the next pointer, and the random pointer. In addition to the val and next attributes, the node class also has the random attribute, which allows the pointer to reference any node in the list or be null. To solve this problem, the output must be the head of the new deep-copied linked list. Let's look at an example. If the input linked list is represented as 7, null, 13, 0, 11, 4, 10, 2, 1, 0, each pair represents a node's value and its random pointer. For instance, the first node has a value of 7, and its random pointer is null. The second node has a value of 13, and its random pointer points to the first node. Similarly, the third node has a value of 11, and its random pointer points to the fifth node. This pattern continues for all nodes in the list. The goal is to create a deep copy of this linked list where the next and random pointers in the new list replicate the connections from the original list, but with entirely new nodes. Now, let's examine the output for the first example. The deep copy of the linked list should look identical to the input, represented as 7, null, 13, 0, 11, 4, 10, 2, 1, 0. The structure of the clone list matches the original. All random pointers in the deep copy point to the corresponding nodes in the clone list, not the original. For instance, in the deep copy, the second node with a value of 13 has its random pointer pointing to the new version of the first node, just like the original. This ensures that the deep copy is completely independent from the original list while maintaining the same structure. Looking at another example, if the input is 1, 1, 2, 1, the random pointer of the first node points to the second node, and the random pointer of the second node points to itself. The deep copy should replicate this structure, so the output will also be 1, 1, 2, 1. For the second example, the explanation highlights that the deep copy is structurally identical to the original list. Here, the first node in the output has its random pointer pointing to the new second node, while the second node's random pointer points to itself in the clone list. This demonstrates that even when random pointers form cyclic or self-referential connections, the deep copy must replicate these connections in the new list. Finally, consider the edge case where the input linked list is empty. If the head of the input list is null, there are no nodes to copy. Therefore, the output will also be null, representing an empty deep-copied list. This ensures that the solution handles cases where the list has no elements. To summarize the constraints and edge cases for this problem, the linked list can have between 0 and 1000 nodes, and the value of each node can range from -10,000 to 10,000. The random pointer for each node may either point to null or to any node within the linked list. Key edge cases include an empty input list, where the output should also be empty, lists where all random pointers are null, which simplifies the copying process, and lists where the random pointer of a node points to itself, introducing a cyclic reference. Additionally, the solution must handle lists with only one node and lists that contain duplicate values. Regardless of the scenario, the deep copy must maintain the exact structure and relationships of the original list, ensuring the new list is entirely independent of the original. To solve the problem of copying a linked list with random pointers, we first consider the brute force approach. This method is simple and intuitive but inefficient. The idea is to iterate through the original list twice. In the first pass, we copy each node's value and next pointer to create a new linked list. In the second pass, we handle the random pointers by searching for the corresponding node in the new list for every random pointer in the original list. To assist with this, we use a hash map to store the mapping between original nodes and their copies. This approach has a time complexity of O(n) squared, because of the repeated searches, and a space complexity of O(n) due to the hash map. While straightforward, this method is too slow for large inputs and can be greatly improved. One way to improve on the brute force approach is by using an optimized hash map strategy. Here, we reduce the inefficiency of repeated lookups by storing the mapping between original nodes and their copies directly during the first traversal of the list. This eliminates the need to search for random pointers separately. Specifically, we traverse the original list and create a copy of each node while storing the mapping in a hash map. In a second traversal, we use the hash map to assign the next and random pointers for each copied node. This approach has a time complexity of O(n), since we only traverse the list twice, and a space complexity of O(n) due to the hash map. It's faster and easier to implement compared to the brute force method, making it a substantial improvement. However, it still requires extra memory for the hash map, which we can aim to eliminate. To achieve optimal efficiency, we turn to the in-place node interleaving approach. The key insight here is that we can eliminate the need for a hash map by interleaving copied nodes directly within the original list. This ensures that the necessary relationships between original and copied nodes are preserved without additional space. The process involves three main steps. First, for each node in the original list, we create its copy and insert it immediately after the original node. This interleaving allows us to use the structure of the list itself to manage relationships. Next, we assign the random pointers of the copied nodes by referring to the random pointers of the original nodes, which now have their copies interleaved next to them. Finally, we separate the copied nodes from the original list to restore the original structure and produce the copied list. This approach has a time complexity of O(n), since we traverse the list 3 times, and a space complexity of O(1), since no additional data structures are used. While it may be slightly tricky to implement, it is the most efficient solution. The in-place node interleaving approach stands out as the best solution due to its optimal time complexity of O(n) and space complexity of O(1). By directly interleaving the copied nodes within the original list, we eliminate the need for extra memory, making this method both elegant and efficient. While the hash map approach is simpler to understand and implement, it requires additional memory, which is unnecessary given that the in-place approach achieves the same result more efficiently. The brute force approach is simply too slow and impractical for larger inputs. The most important realization here is that by leveraging the structure of the original list, we can set up the random pointers without the need for external data structures like a hash map. This insight reduces space usage dramatically while maintaining linear time complexity. Ultimately, the in-place approach strikes the ideal balance between efficiency and elegance, making it the preferred solution for this problem. In this problem, we are tasked with creating a deep copy of a linked list where each node contains an additional random pointer. This random pointer can point to any node in the list or be null. The challenge lies in not just duplicating the structure of the list but also ensuring that these random pointers in the copied list correctly replicate those of the original. To achieve this, we use a hash map, which serves as a dictionary to map each original node to its corresponding copy. This mapping allows us to easily handle the random pointers, even if the nodes they point to haven't been copied yet. The algorithm begins by initializing the necessary data structures, including the hash map, and setting up a pointer to traverse through the original list. The first step is to make a single pass through the original linked list to create copies of all the nodes. As we traverse the list using the current pointer, we create a new node for each original node, copying only its value for now, while leaving the next and random pointers null. Each original node is then mapped to its corresponding copy using the hash map. Once this pass is complete, the hash map contains all the original nodes as keys and their respective copies as values. The second step is to go through the list again and assign the next and random pointers for each copied node. Using the hash map, we retrieve the copy of the current node and set its next pointer to the copy of the next node in the original list, if it exists. Similarly, we set the random pointer of the copied node by looking up the copy of the random node in the hash map. By the end of this second pass, all pointers in the copied list are correctly assigned, and the copied list is fully constructed. The use of a hash map is a key insight in this algorithm. It ensures that each original node is copied exactly once, and the corresponding copy can be accessed in constant time when assigning pointers. This eliminates the need for nested loops, making the algorithm significantly more efficient than a brute force approach. Another important insight is the separation of node creation and pointer assignment into two distinct passes. This ensures that all copied nodes are available in the hash map before we start assigning pointers, which avoids issues where a random pointer references a node that hasn't yet been copied. Additionally, the algorithm gracefully handles edge cases. If the input linked list is empty, we immediately return null. For nodes with null random pointers, we ensure that these are correctly represented as null in the copied list by checking for null before accessing the hash map. The algorithm relies on two main data structures, a hash map and the linked list itself. The hash map is crucial for storing the mapping between original nodes and their copies, allowing for quick lookups during the pointer assignment phase. The final output is a new linked list where each node has the same value, next pointer, and random pointer structure as the original list. In terms of complexity, the algorithm runs in O(n) time, where n is the number of nodes in the original list. This is because we make two linear passes through the list, one for creating nodes and another for assigning pointers. The space complexity is also O(n), due to the hash map, which stores a key value pair for each node in the original list. To see the algorithm in action, let's consider an example. Suppose the original linked list has three nodes, node 1 with value 1, node 2 with value 2, and node 3 with value 3. The next pointers connect them sequentially, and the random pointers are as follows: node 1's random pointer points to node 3, node 2's random pointer points to node 1, and node 3's random pointer is null. During the first pass, we create copies of each node, node 1 foot, node 2, and node 3, and store the mappings in the hash map. In the second pass, we assign the next and random pointers for each copied node. The next pointer of node 1 foot is set to node 2, and similarly, node 2 points to node 3. For the random pointers, node 1 foot is assigned node 3, node 2 is assigned node 1, and node 3 has its random pointer set to null. The result is a new linked list that is a deep copy of the original, with all next and random pointers correctly replicated. Here, we start by defining the node class, which represents the structure of each node in the linked list. Each node has three attributes: val for the value of the node, next for the pointer to the next node, and random for the pointer to any random node in the list. Next, we define the copyRandomList function inside the solution class. This function is tasked with creating a deep copy of the given linked list. The first step checks if the input head is none, which means the list is empty. In that case, we return none. Otherwise, we initialize an empty dictionary called node_map. This dictionary will serve as a mapping between the original nodes and their corresponding copied nodes. We then traverse the original list using a current pointer. For every node in the original list, we create a new node with the same value and store this mapping in node_map. This ensures that each node in the original list has a corresponding copy in the dictionary. By the end of this loop, we've created all the new nodes but haven't yet set their next or random pointers. Once we've created the mapping, we focus on assigning the next and random pointers for the copied nodes. Using another traversal of the original list, we check if the current node's next pointer is not none. If it isn't, we assign the next pointer of the copied node to the mapped copy of the original node's next. Similarly, if the current node has a random pointer, we assign the random pointer of the copied node to the mapped copy of the original node's random. After this loop, all the copied nodes will have their next and random pointers correctly set up to replicate the structure of the original list. Finally, we simply return the copied head node by accessing node_map head. This gives us the deep copy of the original linked list, which includes all the nodes and their respective connections. Here, we begin by defining the structure of a node class, which has three properties: val, next, and random. The val property stores the value of the node, while next is a pointer to the next node in the list, and random is a pointer to any node in the list or null. In the solution class, we define the copyRandomList method to solve the problem. First, we check if the input list is null, in which case we return null immediately. If the list is not empty, we proceed with step 1, which is to create a mapping from the original nodes to their copies. We use a hash map called nodeMap for this purpose. Then, we iterate through the original list using a pointer called current. For each node, we create a new node with the same value and store this mapping in the hash map, where the key is the original node, and the value is the copied node. After creating the mapping, we move to step 2, where we assign the next and random pointers for the copied nodes. We reset the current pointer back to the head of the original list and iterate through it again. For each node, if it has a next pointer, we update the next pointer of the copied node by looking it up in the hash map. Similarly, if the node has a random pointer, we update the random pointer of the copied node using the same mapping. Once all the pointers are assigned, we proceed to step 3, which is to return the head of the copied list. We do this by retrieving the copied node corresponding to the head of the original list from the hash map. This completes the implementation of our solution. To solve the problem of copying a linked list with random pointers, we'll start with a simple example where the linked list has no random pointers. The input consists of 3 nodes connected sequentially, 1 points to 2, 2 points to 3, and 3 points to none. First, we initialize an empty mapping called node_map to associate each original node with its copy. We also set a pointer, current, to the head of the original list, which is node 1. In step 1, we begin creating copies of each node. For node 1, we create a new node with value 1 and add this to node_map with node 1 as the key and its copy as the value. Similarly, we process node 2 and node 3 in the same way, adding their respective copies to node_map. At the end of this step, node_map contains mappings for all nodes, node 1 mapped to its copy, node 2 to its copy, and node 3 to its copy. This establishes the foundation for linking the copied nodes together in the next steps. In step 2, we assign the next and random pointers for the copied nodes using the mappings in node_map. Starting with node 1, we set its copy's next pointer to the copy of node 2, which is stored in node_map. Since node 1 has no random pointer, we leave the copy's random pointer as none. Next, for node 2, we set its copy's next pointer to the copy of node 3, and again, the random pointer remains none since the original node 2 has no random. Finally, for node 3, we set its copy's next pointer to none, as node 3 is the last node in the list, and there's no random pointer to assign. In step 3, we return the copied head, which is the copy of node 1 retrieved from node_map. The result is a new list identical to the original, with sequential nodes and no random pointers. Now, we'll look at an example where random pointers are present. The input contains 3 nodes connected sequentially, just like before, but now the random pointers add complexity. Node 1's random points to node 3, node 2's random points to node 1, and node 3's random points to node 2. In step 1, we initialize node_map as an empty dictionary and set current to the head of the original list. As we traverse the list, we create copies of the nodes just like in the simple example. For node 1, we create a copy and add it to node_map. We repeat this for node 2 and node 3, resulting in a complete mapping from the original nodes to their copies. At this stage, node_map is populated with copies of all nodes, ready for the next step where we handle both next and random pointers. In step 2, we assign the next and random pointers for the copied nodes. For node 1, its copy's next pointer is set to the copy of node 2, and its random pointer is set to the copy of node 3, as indicated in the original list. For node 2, we set its copy's next pointer to the copy of node 3, and its random pointer is set to the copy of node 1. Finally, for node 3, its copy's next pointer is set to none, and its random pointer is set to the copy of node 2. This ensures that all connections, including the random pointers, are correctly replicated in the copied list. In step 3, we return the copied head, which is the copy of node 1. The copied list now matches the input structure, including both sequential and random connections. In the third example, we examine the simplest case, a single node where the random pointer points back to itself. The input consists of node 1 with no next pointer, and its random pointer references itself. In step 1, we initialize node_map as an empty dictionary and set current to node 1. We create a copy of node 1 and add it to node_map, establishing a mapping from the original node 1 to its copy. In step 2, we assign the next and random pointers for the copied node. Since node 1's next pointer is none, the copy's next pointer is also set to none. For the random pointer, because node 1's random points to itself, the copy's random pointer is set to point to itself as well. Finally, in step 3, we return the copied head, which is the copy of node 1. The result is a single node list where the random pointer correctly points back to the node itself. In this problem, the time complexity of our solution is determined by two main steps. First, we create a mapping of the original nodes to their corresponding copied nodes. To achieve this, we traverse the original linked list once, processing each node exactly one time. For every node, we create a copy and store it in a dictionary called node_map. This traversal takes n time, where n is the number of nodes in the list, and each dictionary operation, such as storing the copy, is performed in constant time, 1. So, the total time complexity for this step is n. Next, we assign the next n random pointers for the copied nodes. This requires traversing the list again, and for each node, we access its next n random pointers through dictionary lookups, which also take constant time per node. Since we traverse the n nodes once more, this step also takes n time. Summing up, both steps contribute n each, making the time complexity for the solution proportional to n. Now, when we consider the overall time complexity, we see that each of the two steps involves a single traversal of the list and performs constant time operations for each node. Adding these together, the total time complexity becomes n plus n, which simplifies to n. Shifting focus to space complexity, the solution requires additional space for the node_map dictionary and the new nodes that we create. The node_map dictionary stores a mapping of each original node to its corresponding copied node, and since there are n nodes in the original list, the dictionary occupies n space. Similarly, each copied node is a new object in memory, and since we copy all n nodes, the space required for these copied nodes is also n. Therefore, both the dictionary and the copied nodes contribute n space each. Additionally, the algorithm uses a constant amount of extra memory for temporary variables like current, which is used to iterate through the list. This means that the space usage for such variables is 1. When we combine all the space requirements, including the dictionary, the copied nodes, and the constant space for variables, the total space complexity becomes n plus 1, which simplifies to n. This shows that the space complexity is primarily driven by the dictionary and the storage of new nodes, both of which scale linearly with the size of the input list. To put this into perspective, let's compare our optimized approach to a brute force method. A naive approach might involve creating new nodes and manually iterating through the list to find the correct random pointer for each copied node. This would require an n traversal for determining the random pointer of each node, resulting in an overall time complexity of n squared. However, the space complexity in this brute force approach would still be n, due to the storage of copied nodes. In contrast, our optimized approach uses a dictionary to map original nodes to their copies, enabling constant time 1 assignment of random pointers for each node. This reduces the overall time complexity from n squared to n, while the space complexity remains n, making the optimized solution far more efficient. Finally, let's analyze the algorithm's performance for the best, average, and worst cases. Regardless of the structure of the linked list, the time complexity remains n, as each node is processed exactly twice, once during the creation of the mapping and once during the assignment of pointers. Similarly, the space complexity is n, in all cases because of the dictionary and the new nodes that are created. Therefore, the algorithm is consistent in its efficiency, with n time and n space being the best, average, and worst case complexities. This consistency makes the solution highly reliable for linked lists of any size or structure. When solving the copy list with random pointer problem, there are a few common mistakes to watch out for. First, ignoring edge cases like empty lists or lists with only one node can lead to issues such as null pointer exceptions or incorrect results. To prevent this, always start your implementation by explicitly handling these edge cases. Another frequent mistake is modifying the original list instead of creating a separate copy. This violates the problem constraints and can introduce side effects when the original list is reused. A good practice here is to use a separate data structure or explicitly clone each node. Finally, relying on inefficient nested loops in a brute force approach is another pitfall. While this might seem straightforward, it leads to a time complexity of n squared, which is impractical for large inputs. Instead, optimize your solution with auxiliary data structures like hash maps or by using a two-pass approach to improve efficiency. Incorrect pointer management during the copying process is another common issue. When copying nodes, if the next n random pointers aren't updated correctly, the resulting linked list might be broken or even cyclic, leading to incorrect outputs. To avoid this, it's crucial to carefully manage these pointers and validate your implementation with small test cases. Another point to consider is the space complexity of your solution. While using hash maps or other auxiliary data structures can optimize time complexity, they come at the cost of additional space usage. For large inputs, this can result in memory constraints. It's important to evaluate the trade-offs between time and space complexity and choose an approach that aligns with the problem requirements. Balancing these aspects ensures a robust and scalable solution. In interviews, understanding the problem constraints is key. For example, interviewers often test your ability to handle edge cases and ensure the original data structure remains unmodified. It's also helpful to communicate the trade-offs in your approach, such as time versus space complexity, as interviewers value your ability to analyze and justify your decisions. Additionally, always test your solution with a variety of edge cases, like empty lists, lists with cycles, or those with duplicate values. This demonstrates thoroughness in your problem-solving process. Another effective strategy is to optimize iteratively. Start with a straightforward brute force solution and then refine it step by step. Interviewers appreciate seeing your thought process and how you improve on initial ideas. Finally, familiarize yourself with common patterns, such as two-pointer techniques, hash maps for auxiliary storage, and recursive approaches, as these are often applicable to problems involving linked lists. The concepts in this problem are closely related to other linked list problems, such as LeetCode 206, reverse linked list, and LeetCode 160, intersection of two linked lists. Exploring these can deepen your understanding of linked list manipulation. When it comes to alternative approaches, a brute force method using nested loops is a straightforward option. While simple to implement, it's inefficient with a time complexity of n squared, so it's mostly suitable for small input sizes where performance isn't critical. A more efficient approach uses a hash map to maintain a mapping between original and copied nodes. This achieves n time complexity but requires n additional space, which is acceptable when memory constraints aren't a concern. Another option is the two-pointer technique, which reduces space usage but requires careful pointer management to ensure correctness. This is ideal when optimizing for space efficiency. A recursive approach can also be used to solve this problem. This method is elegant and concise, as it leverages the inherent recursive structure of the list. However, it's important to consider the trade-offs. Recursion can lead to stack overflow for large input sizes, especially if the recursion depth exceeds the system's limits. This makes it less suitable for scenarios where the input size is unpredictable or very large. On the other hand, if the recursion depth is manageable, this approach can simplify the implementation and make the code easier to read. Recursive solutions are particularly useful in problems that naturally lend themselves to divide-and-conquer strategies or when readability and simplicity are prioritized over handling extreme edge cases. Great work reaching the end of this walkthrough. To summarize, we covered the problem, explored the efficient approaches, and discussed the key takeaways. Remember to practice linked lists and hash map-based problems to excel in technical interviews. Thank you for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!